Hello, everyone. Welcome to what will be pre-lecture 26 today. We're delving into chapter 17, our last chapter for the semester, looking at oxidation reduction reactions and ultimately electrochemistry. So hopefully something that is review from General Chemistry 1 is discussion of redox reactions. So oftentimes we abbreviate them as redox because they involve both reduction and oxidation. Just a reminder as well that you cannot have reduction without oxidation or oxidation without reduction. You need both to go together. That's why we call them redox reactions. Also a reminder that a reduction of something means a gain of electrons. So even though we're gaining electrons, it is reduction because we are reducing the charge overall. Because electrons are negatively charged, the charge goes down when we gain electrons. Oxidation is the opposite of that, of course, where we have the loss of electrons leading to a more positive charge. If you have trouble keeping those straight, a handy acronym is OIL rig. So OIL stands for oxidation is loss of electrons. Then rig is reduction is gain of electrons. So if you ever have trouble remembering that, just remember OIL rig. Also within redox reactions, another way we could define things is the compound that gains electrons is the oxidizing reagent. That means that the oxidizing reagent is reduced during a chemical reaction. And then, of course, the opposite is true where our reducing reagent is oxidized. The reason we define things this way, we would say that our oxidizing reagent is the thing that does the oxidizing, and thus it is reduced itself. Okay, so I know that can be a little difficult to keep straight, but a good thing to practice with and remember throughout this chapter. Okay. Finally, why would we care about redox reactions? These are actually extremely important, especially in the construction of batteries that are, in our world in 2021, help us function every day. If you're watching this on a phone or a laptop, you can thank a battery for that. And then, of course, redox reactions are also aplenty in many biological processes. Okay. So a couple things we're going to go over today are determining oxidation states and then balancing redox reactions. And so reminder that an oxidation state is a measure of the number of electrons relative to the number of protons within an atom. And so there are some tricks to assigning oxidation states, particularly for compounds. And so you want to follow these rules. First rule is that, and I should say before I get into these rules, that these are in order of most importance. So rule number 1 would trump rule number 2, 3, 4, 5, and so on. So the order of these rules does matter. So with that, again, our first rule is that free elements have an oxidation state of 0. This can also include mono and diatomic elements. So if you have something like nitrogen gas, N2, that has an oxidation state of 0 because it is considered a pure element. Our next rule is that monoatomic ions, so things that are charged, have an oxidation state equal to their charge. And then if you have a salt, so a combination of atomic ions, then the sum of the oxidation states is equal to 0 if the compound is neutral. If you have something like a polyatomic ion, something like sulfate, SO4 2-, then the rule is that the oxidation states of all the atoms within the polyatomic ion must be equal to the charge of the overall ion. We'll do a little bit of practice with that in class. Okay. Our third rule is that group 1 and group 2 metals, so these would be the first 2 columns on the periodic table, have oxidation state corresponding to their place in the periodic table. So that would mean elements in group 1, which is again our first column on the periodic table, would always have a charge of +1, unless they are in their pure elemental form where they don't have a charge, in which case it would be 0, of course. And group 2 metals will have a charge of +2. Okay. Rule number 4 is that some elements almost always have the same charge. If we list them with their relative priorities, fluorine will always have a charge of -1. Hydrogen pretty much always has a charge of +1. Something I should say, just a reminder, again, rule number 1 would trump rule number 4. So if fluorine is F2, it would have an oxidation state of 0. Hydrogen were H2, it would have an oxidation state of 0 as well. But if hydrogen is bound to something else, it should have a charge of +1. Next up, oxygen almost always has a charge of -2, unless it is a peroxide, in which case we have two oxygens that are bound together that are also bound to other things. So hydrogen peroxide is a classic example where we have H2O2. In that case, oxygen's oxidation state would be -1. Then for our last rule, group 17, which are halogens, have a -1 charge. Group 16 have a 2- charge, and group 15 have a 3- charge. Generally speaking, those, of course, are some of our lowest priority, and so they can be overcome by those other rules. Finally, all other oxidation states should be able to be determined based on following rules 1 through 4. Okay, and we'll get plenty of practice with this in class. Along with assigning oxidation states for just compounds or elements, we can also then balance redox reactions in a systematic manner. And so in order to do that, the first step would be to determine the oxidized element and the reduced element. From there, you would write the oxidation reaction and the reduction half reaction, and you would want to include the number of electrons for each of those. Okay. With that, you want to balance the elements that are oxidized and reduced. This will typically be all the elements that are not oxygen and hydrogen, although, of course, oxygen and hydrogen can be reduced or oxidized as well, but typically it will be the non-oxygen and hydrogen. Then you'll want to balance any oxidation states by adding the electrons. Okay, and I'll go through an example in this video of this. Our third rule is to balance the charge of the half reactions by either balancing it with H+ or OH-. So with all of these redox reactions, I will tell you to either balance it in acidic or basic solution, and you would do that by adjusting the charge with those either H+ or OH-. Next, you would balance any oxygen atoms and with that hydrogen atoms by adding water. Whoops. And then number 5, you'll want to balance the electrons between the two half reactions. So they might have different number of electrons, in which case you need to balance those. And finally, add the two half reactions together and add any phase labels as well. Okay. You can always do a check. So the great thing about these problems is that they are self-checking, and the number of atoms and charges should be the same on both sides. That's just basic stoichiometry. Okay, so let's do an example of this. If you want to do this practice problem by yourself first, you of course can. Otherwise, I will start to go through it right now. So we have bromate, our molecule here, and we will be reacting that with hydrazine. So N2H4 is actually rocket fuel, and we will be having this redox reaction. So if I go through and just start to try and assign oxidation states here, I know from our rules, oxygen should always have a charge of 2- because we have 3 oxygens. That means our total oxygen charge should be 6-. Because we need our overall charge of BrO3- to be -1, that means the oxidation state of bromine will be +5. Okay, because +5 and -6 equals -1, which is, again, the overall charge of our ion there. Okay. For N2H4, we know hydrogen should always have a charge of +1, and we have 4 of those hydrogens, so we should have an overall charge of +4 from that. Because our molecule is neutral, we know that the 2 nitrogens will need to have an overall charge of 4-, and because we have 2 nitrogens, we know that we could do 2 times 2- in order to get -4. So that means that the oxidation state on nitrogen is 2- in this side of the equation. If we look at our products, we should see a change in oxidation state. So bromine here is just, or bromide, I guess I should say, is just -1. So we get a change from +5 to -1 for our bromide, meaning that our bromine is going to be getting more negative, meaning that that is going to be our reduced species. And then our N2 is going from a charge of 2 minus, we said, to a charge of 0. Because again, with N2, that's pure element, so nitrogen will be oxidized over the course of this reaction. Okay. Right. So from there, we'd split these into two separate reactions. So if we start with the reduction half reaction, that would be starting with our BrO3 minus, and we know that it is eventually turning into bromide. Okay? And so if we go through the steps of trying to balance this, we said we're going from an oxidation state of +5 to -1. That means in order to do that, we need 6 electrons on our reactant side in order to get change the number of electrons in order to balance them. Because to go from +5 to -1, we need to add 6 electrons by the time we get to our products. So that balances our electron charge. We then need to balance the charge between the sides. So of course, our left side is going to be, oh, I forgot my minus charge there. It's going to be 7 minus total and 1 minus on our product side. And so we could add 6 protons if we're balancing this in acidic media, so that we have an overall charge of -1 on both sides. Okay. Finally, we want to balance this out with water. And so to our product side, we would add 3H2O. That gives us 6 hydrogen, which would balance with 6 hydrogen on our reactant side, and then 3 oxygens, which would balance with our oxygens on our reactant side. Okay. So we've now balanced our reduction reaction. So now let's balance the oxidation reaction. And so for this reaction, we said we have N2H4 that is turning into N2. We said that this is going to be an oxidation. So again, nitrogen on our reactant side has an oxidation state of 2 minus, and it's going to an oxidation state of 0 on our product side. So if we try and balance our electrons, going from 4 minus to 0, we have 4 electrons we would need to put on our product side because that is the side with less electrons. And then we can balance our charge by adding 4 protons as well. Right? And in this case, this actually balances all of our elements, so we don't have to add any water in the case of our second oxidation reaction here. Okay. So now to put these back together, we have to have the same number of electrons. And so we look for the lowest common denominator here of where both of these would be. The lowest common denominator would be 12 for these two for these two balanced reactions. And so we would multiply our top reaction by 2. We would multiply our bottom reaction by 3 in order to get the number of electrons to be the same. Okay, and so if we recombine them, we should get something like 12H plus 12 electrons plus 2BrO3 minus plus 3N2H4, and that produces 2Br minus 3N2, and then 12 protons, 12H plus. Oops, sorry about that. Let me just erase that so it's clear. 12H plus, and then 12 electrons, and finally a total of 6 waters. Right? Okay, and so we can cancel out like terms between our products and reactants. Our electrons should always cancel, so we can cross out our electrons. In this case, we actually cross out our protons as well. So we have 12 protons on each side, so we can cross those out as well. And so our final reaction should be 2BrO3 minus plus 3 N2H4 yields 2Br minus plus 3N2 plus 6H2O. We can double check this and see that our number of atoms for each side also check. So 2 bromides on each side. We have 6 oxygens, 6 oxygens, 6 nitrogens, 6 nitrogens, and then 12 hydrogens, 12 hydrogens. So everything checks. We have a happy puzzle piece for those of you that maybe like Sudoku or crosswords. I hope this is equally as satisfying. Okay. All right, that was balancing redox reactions. I hope that was helpful. If you have any questions, of course, feel free to email. Otherwise, you can always ask me in class as well. Take care, and I will see you in class on Thursday.